Hi, welcome to another video on solutions to AEC and ME. In this video, we'll see ADC based design problems. So, in the first problem, we are asked to find what is the conversion time of this DAC based ADC. The specification given are the conversion time of this DAC is 35 microsecond. The clock to Q delay of the counter plus logic is 25 microsecond, and we have the delay associated with op amp as 10 microsecond. So now we will see how to address this issue of finding the conversion time in a DAC based ADC. Okay, this is the block diagram of a DAC based ADC, which we know in theory it consists of a counter plus logic and a DAC. The output of the counter is given to the input of the DAC. The output of the DAC is going to a comparator where it is compared with the input voltage. If the input is more than the DAC output, suppose if I say this is my DAC output V0, if Vin is greater than V0, then you are allowed to counter, you will up count the counter. Otherwise, you'll stop the counter and then get the EOC. Actually, the process starts like this. So now, okay, assume that this is the start signal. As long as start signal is 0, the conversion will not start. So once you make the start signal high and then make it low, this will initiate the counter from. Counter will start counting from. So this is your counter. Suppose if you say counter, the counter is 0 here. From this count onwards, so here it is 0 0. From this count onwards, so this starts counting from 0. Of course, you have a clock coming all the time. So this is the clock. This is the clock what you're getting. This is the clock which is coming. Now, whenever, of course, if this is a positive edge clock, upon giving this, so after this edge, after this positive edge of the clock, this is clock, the counter will increment from 0 to, it will become 0 1. Okay, let me just okay, this is of course, let me just say this is binary, decimal equivalent of depending on the number of bits you have 0 0 1, or suppose if it is 8-bit counter, it will be of the first clock, it will be 0 0 0 0 and then 0 0 0 1. After the second clock, it will be 0 0 0 0 and then 0 0 1 0. So this is how it keep on incrementing. So after every positive edge, this is going to include, this is going to increment, the count is going to increment. But the catch here is, of course, this will continue till your this output becomes high, so that this will going to stop the count. So the counter output will be your ADC output, equivalent to your analog input voltage. Now the point is, before once this count is incremented, before this counter increments to the next number, we have to have the decision made here. That is, the clock frequency cannot be very high. That is, the time at which the next clock pulse comes, by that time the data should be ready here whether to up count or stop the count. Meaning, upon giving the start, upon the first clock edge, so the counter will take some time to go upon giving the clock to get the output. It takes some time, that is known as clock to Q delay. So this Q is nothing but the output of the counter, because we know that counters will have outputs. So we usually write it as Q0, Q1, Q2, Q3. So these are the outputs of the counter. So clock to Q delay is upon giving the edge of the clock. So how much is the time taken by the counter to up count to respond to that clock. So that is what is clock to Q delay, which is 25 microsecond in this particular specification. And once you give the input combination of whatever digital combination, this will not give the output immediately. Now it is taking 35 microsecond as per the specification. So once you have some value over here and it is compared with this will also not give immediately. It is taking 10 microsecond. So before my next clock pulse come, that is, this is my first edge, before my next edge comes. So I have to complete this, all the three processes have to be completed before I get the next clock pulse. Suppose if I say this is my T clock, if this is my T of the clock, so T clock should be certainly greater than the summation of all the three timings. So T clock should be greater than T clock to Q delay plus T of the DAC plus T of the op-amp. So these put together, which comes out to be 70 microsecond here. So this is 70 microsecond, which is the summation of all the three. 25 plus 35, which is 60, 60 plus 10 is 70 microsecond. So my clock frequency should be more than 70 microsecond. If it is less than 70 microsecond, then the data will not be ready here to upcount or do whatever the thing. So it will not be considered, or that particular clock will be, assume that this is hardly 50 microsecond. If it is 50 microsecond, by this time it will not count up because the decision is not yet made. So here it is not allowing you to count up because data is not yet ready. So now that's why to have a clock frequency sufficient enough more than greater than 70 microsecond in this particular example. So keeping this in mind, the conversion time should be more than, of course, what is conversion time? So because we know that in your DAC based ADC, the conversion time depends on what is the input amplitude. If the input amplitude is more, then it takes more number of cycles to upcount to that number. If it is less, then it takes lesser time. So it is depending on the input voltage, the conversion time will going to happen. Now let us take that example here. What should be my T clock? T clock should be less than 70 microsecond. So let us consider first example here. So in this first specification, the input voltage given is 3.2 volts. The number of bits of this ADC is 8 bit. I am finding what is 1 LSB. So 1 LSB is nothing but 2 power. So what is 1 LSB? 1 LSB is actually V reference by 2 power n. So this is V reference by 2 power n. In this case it is 5 by 256. 5 by 256 happens to be 19.53 millivolt, and this 3.2 volt I am writing in terms of LSBs. How many LSBs is 3.2 volts? So for that I am writing, I am just obtaining this 164 by V in, that is 3.2 divided by 19.53 millivolt will become 163. You just round it up to the next number. This is 163. Now the clock frequency given is 10 kilohertz. The clock period becomes 100 microsecond. If you can see this, for this specification, I want to have a clock period should be more than 70 microsecond. Since my clock period is 100 microsecond, which is certainly more than this. Oh, this should be more than. I'm writing it differently. So P clock should be greater than 70 microsecond. It's not less than. It should be greater than 70 microsecond. So is it 100 microsecond? So by the time the next clock comes, the decision will be made here to go for next count or to give a EOC. So then what is conversion time? The conversion time is given by the number of LSBs for the given input multiplied by the clock frequency, clock time period. So clock time period. Is it not? So how many LSBs are required? So it has to increment 164 times multiplied by 100 microsecond. 100 microsecond. So this is my conversion time. So conversion time happens to be 1.6. Okay, 164 into so on. So if you see this, can you see this is 16.4 millisecond, because that is 16.4 millisecond, because this time period is more than 70 microsecond. Next, let us see what happens. Next, let us consider one more case. It's the same input voltage, same number of bits. When number of bits are same, V reference is 5 volt, and can you see LSB is still same? Since the input is same, it is same 164, but the frequency is now 100 kilohertz. When the frequency is 100 kilohertz, the time period for each period of the clock is 10 microsecond. So we know that it requires minimum 70 microsecond to get the response from the entire network. So if you keep giving the clock pulses very repeatedly before it completes the process, it will not take. So then conversion time is not this N1 into T clock. It is not. This is N1 into T clock as long as T clock is having a time more than the summation of all the propagation delays. Now, since it is taking 10 microsecond only, I will not get the output immediately. By the time I will get the next clock pulse. So it is now 164 multiplied by time required for each one of them to response, that is 70 microsecond. So that comes out to be, okay, I don't have a calculator now, so that's I'm just showing you this. Sorry for that. So it is taking, let me just stop this. This is taking 11.48 milliseconds. This 11.48 is nothing but 164 multiplied by 70. So let me just do it using my CAD in my mobile. So how much is this? So this is now, sorry for that. This is, okay, how much time I take now is, so it is 164 multiplied by 70 micro, which happens to be this into micro, this into 10, okay, to the power of, that is to the power of minus 6. Okay, now can you see this is 11.48 millisecond. That's what it is, 11.48 millisecond, which is there here, which is there 11.48 millisecond. So that's the time now it is taking. So it's not like okay 10 microsecond into 164. It is not 10 microsecond to 164 because this is coming too fast. You can't take that. So on the same lines, let me just see this. See now, it is 1.6 volt. Number of bits are 8. One LSB is 19.53. The number of LSBs corresponding to 1.6 will become 82. Since the clock frequency is 100 kHz, the clock period is 10 microsecond. Since this 10 microsecond is less than 70 microsecond, this 5.74 is actually 70 microsecond into 84. So if I do 70, if I just do this, okay, let me clear this. Now what I do is, it is now 70 into 86. So it's, if you can actually go there and then see, is actually, is it not 86, 82. So it's very 82, how do I make it? This is 82. So if it is 82, can you see that time is 5.74 millisecond, because I need to make it 10 power minus 6, so that will become how much? 5.74 millisecond. That's what it is, 5.74 millisecond. So likewise, you're doing this. If the input voltage is 4.8 analog voltage, if the number of bits are 10, one LSB is this. So this corresponds to 4984 LSBs if the clock frequency is 10 kHz. Now you can see when it is 10 kHz, this is 100 microsecond. Now it is 100 microsecond into this much. 100 microsecond into 984, which happens to be 98.4 millisecond. On the same lines, you can do this. So this is a summary. The conversion time is number of input in LSBs multiplied by the clock period if the clock period is greater than 70 microsecond. if the clock period is less than 70 microseconds, then it is n1 into 70 microseconds. Why this 70 microseconds is because that is actually the summation of all the propagation delays. Hope this is fine. Of course, we are finding this n1. Of course, in this case, n1 is nothing but input in LSBs. So this is exactly V in divided by LSB. LSB is actually V reference by 2n, so 2 power n. So that is this equation. Okay, fine. So then we just go to the next problem, where we have. So we are asked to find the value of digital output for an input voltage of 1.08 volt with successive approximation type of ADC. So this is what is successive approximation type of ADC. It is similar to the this is also a DAC based ADC, but only thing is that the increment of the counter will not happen one by one. That is, it's not starting from 000 to 111 with an increment of 1 LSB. It happens in totally different fashion. It starts with MSB first. It compares if it is more than if it is less than the input voltage, you retain the MSB and you update the next lower MSB. Then you start comparing. If the comparison indicates that the output of your DAC is still less than this input voltage, then you just again increment the next lower MSB. So that's how it happens. That will continue till the all 8 bits or all n number of bits are covered. So let us take up this example. So now we have 1.08 as the input voltage. So as I said, you start with this as 1 0 0 0 0 0 0 0. So this 1 0 here I have written the corresponding voltages of these bits. So it is 5 by 2, 2.5 volts. This will be 1.25 volts. This will be 5 by 8, 5 by 16. These are the voltage levels corresponding to these bits. So if you can see there, so this will become. Okay, just give me a minute. Let me get the calc. Okay, now I'm with the calc. Okay, we know that since it is this, this will be 5 by 2. This is 5 by 2. It will be 2.5. This is 2.5. This V0 dash is the output voltage. Sorry, the output voltage of this DAC. Since of course here I had it as 1.08. Now this is 2.5. So this Vx has become high. So the action that should happen is, because the DAC output is more than the input voltage, I have to discard this and make the next MSB as high. So action is you discard the bit. So I am discarding the bit. So I am discarding this bit and making this as 0, and I'll make this as 1. So now this is the thing. So now what I'll do is, so this is now 0. I'll make it plus 5 by 4. So now I know that this is 1.25. This is 1.25. So since this 1.25 is still more than 1.08, I have to discard. So this is high, I want to discard. So I want to, when I say discard, I want to discard this bit. In the next action, I will make the next bit as 1 and I'll do this. So now what I'll do, I'll just go back here and make this as 0 and make this as plus 5 by 8, because this is 5 by 2, 5 by 4, 5 by 8. This is made 0, this is also made 0. This is now 5 by 8. So it is now 0.625. Since this 0.625 of this is less than 1.08, so this is now low. When this is low, you retain that incremented, whichever bit you made high, you retain this and you make the next bit also 1. So it is, you retained it. I'm making this also 1 in my next MSB bit. So now this was retained as 1 now. Now I will add plus 5 by 16. This is now 5 by 16. 5 by 16. What is the value? Now it is 0.93 1.9375. Since this 0.9375 is less than 1.08, I will still the output of Vx is low now. You retain the bit which was made high, then you make the next increment. Now you make this one 0 0. So now what should happen? So this corresponds to what? 5 by 32. So let me just go here and add plus 5 by 32. So what is the value? Now it is 1.09375. So since this 1.09375 is more than 1.08, I have to make this high, so I have to discard. So this is discarding. Here also discarded the previous two discards, so I have to discard this. So I have to discard this and then make this 0 0 1 1 0. Now we make this. So in our bit, so last this 5 by 32, I'll make it as 0 by 32. Okay, I'll make this 0 by 32. Next I'll add next one, it is 5 by 64. If I make it 5 by 64, now you can see it is 1.0156. Now since the comparison of this 1.056 with 1.08 is low, I'm going to retain. So this I'm retaining here. If I retain, the next bit would be 0 0 1 1 0 1. Make this also 1. This is stage 0 now. So what I have to do now? This is actually 1 corresponding to 5 by 128. So let me add that 5 by 128. So I will add plus 5 by 128. So it is now 1.0546. So this is still less than 1.08. The output of the comparator is low. You retain the bit. So I'll retain this bit and I'll make this as, so this is now 1 1 0 1 1. You till here you retain and then you make this also 1. So this is actually 5 by 256. So to this earlier value you add 5 by 256 plus 5 by 256. So what is the value? Now it is 1.0742, which is now, this will give again low. You retain. But after retaining, you don't have any more increment of any more LSBs are not available. So this is my final output. So after all 8 bits are retained or discarded, your successive approximation ADC will give you a EOC signal saying that end of conversion. It gives this as the output, which is 0 0 1 1 0 1 1 1. So just for verification, let us find out this 1.08 corresponds to how many LSBs. So this is now 1.08 into 256 divided by 5 will be the number of LSBs. Okay, let me just find out. So it is 1.08 into 256 divided by 5. Can you see it is now 55.29. If it is 55.29, it will be rounded up to the lesser number, which is 55. Let us find what is now conversion of okay, let me just say decimal. 55 equals, let me find its binary. Can you see now it is, what the binary equivalent? It is now 11011. This is what is 55 equivalent. So since I have to represent it by 8 bits, this is 246. So these two are 8. Is this for 1.08 old, which is 55 LSBs with V reference as 5 volt and number of bits as 8. You see, do we have the same number? 0011 0111. Sorry, just see here. So this voltage 1.08 volt corresponds to 55.29 LSBs. Now round it off to the lesser number, 55 LSB. So why lesser number is because it is, if it is more, you are actually discarding that bit number. So that's why it is a lesser number. So I'm trying to find what is the binary equivalent of 55, which is 110111. So it is 110111. So I'll just make it 8-bit by adding 2 more zeros. So this way we can able to find the digital output of an analog input using successive approximation process. Let us just do one more. So now let us start with this. Okay, we'll be starting with this as 1 0 0 0 0 0 0. I know that this will be 2.5 volt. Since this 2.5 is less than this will be low, you retain. So let me say R for retain, D for discard. So it is now 1 1 0 0 0 0 0 0. So let me again start with that. It was 5 by 2 plus 5 by 4. Sorry, this should be made in. So it's 5 by 2 plus 5 by 4. Sorry. Can you see it is now 3.75, but it is 3.82. It will be still low. You retain. Now you make this next bit also high. So what is this now? Plus, sorry. Let me make this 5 by 2 plus 5 by 4 plus 5 by 8. Can you see now it is 4.375. This is high. You discard this and make the next bit as. So what I'll do, I'll discard this but add plus 5 by 16. How much is that? It is 4.0625. This is still higher than this 3.82. You again discard this, and discarding this 1 1 so 0. Now you make the next bit as high. So I will make this is what, 5 by 16. I'll make it 0 by 16 because that was discarded. Now it is 0 by 16. Next it is plus 5 by 32. 5 by 32. Now it is 3.96. It is still greater than that. This is high. You want to discard. So I have to discard this also. Now it is 1 1 0 0 0 1 0 0. So I have to discard this 5 by 32. Where is 5 by 32? Okay, I'll make it as 0 by 32. Now this will make our process easy. So plus of this is actually 5 by 64. 5 divided by 64. So it is actually 3.828. This is still greater than this. Actually 3.820, but this is now 3.828. You can go up to the third decimal so that because there is no question of equals. So suppose if you take this 0.82, that as 0.82, then you have it equal. So in a comparator, if it is equal, you don't know what the value is. So you still go deeper into the higher resolution, find out which is more, because I need to have this as low or high. So this will be low if V naught dash is less than V in. Suppose if V naught dash is more than V in, it will be high. If it is equals, you don't know. So that's why the equal condition will never exist in electronics. So we need to find out even at microvolts and nanovolts which is more, which is less. So that has to be very clear. So since it is more, you discard this. So if I discard, this is 0 now. 1 0 0 0 0 1 0. So I'll discard this 5 by 64. Let us make 5 by 28. Okay, this 5 by 64, I'll make it 0 by 64. Next it is plus 5 by 128. So it is now, this is fine. 3.789. This is low, you retain. I'm retaining because this is less than 3.82. Now it is 1 1 0 0 0 0. Retain this, make this bit also 1. if I make that bit also 1, so this value corresponds to 5 by 256. I'll retain this 5 by 128 and I will add 5 by 5 divided by 256. So can you see now it is 3.8085. So this is certainly of course less than this. So is it now low? Shall I retain? So this is now 1 1 0 0 0 0 1 1 is your final answer. Let us find, okay, let us verify whether this is fine or not. So 3.82 corresponds to how many LSPs? It is 256 by 5 is those many LSPs. So I'll make it 3.82 into 256 divided by 5. Is it actually 195.58? So you round it off to a lower LSP, this 195. So this 195 corresponds to how many, what is that? Binary. So it is mod 3. Now you are there in decimal. 195 equals binary. So can you see now this is 11000011. We have the same number. 11000011. So this is matching with this. So that's the way how we can do it. Okay, let me just show you the one more problem, okay, which is on the same lines. So you can take 2.16. You start with 2.5. You are discarding because it's more than that. So it's exactly the same process. So here we have the action as V naught dash is nothing but voltage. V naught dash is what? This is voltage in. Of course, the action that we are taking here is. Oh, sorry, this is not V naught dash. I don't know why I wrote it as V naught dash. No, this is not V naught dash. This is actually number of LSPs. No, this is not V naught dash. Sorry, this is not V naught dash. Okay, let me just. Okay, the action that you. Okay, V naught dash is actually what? Not V in. So this by. Okay, if it is 1, as I just mentioned here, what is V naught dash now? V naught dash is actually 5 by 2 here. Here it is 5 by 2 plus 5 by 4, and here it is again. You can see I'm just making this plus this plus this. So the weight of this is 5 by 2. Weight of this is this. Weight of this. Okay. Then okay. Let us see. There is one more problem. We are asked to find out E and OB. So let us just speak about this E and OB for a minute. For that I need an interesting images I want. Just have a look at this. Okay, before this let me show you this also. Okay, 1 second. Let me just open this. Let me open this also. There is one more. Sorry. I think I can move here. Okay, fine. We know that this is your ADC. You have an input voltage. You have to give a start conversion. So depending on the conversion value, whether it will be incremented to next number, or that's how it happens. So you finally get the UOC. I think maybe you might have learned all these things. If the input voltage is less than, of course this is 1 LSB. So this is 1 by 8, 2 by 8, 3, 8. So actually 1 by 8 is 1 LSB. This is 1 LSB, 2 LSB, 3 LSB, up to 7 LSBs. These are all the digital outputs. Suppose if the input is, let me just further zoom it up. So this is my input. If the input is less than 1 LSB, so okay, let us take it as this is half LSB. If the input is less than half LSB, you are still treating it as 0, 0, 0. If the input is somewhere here, you can see, suppose if the input is 0, then it is 0. If the input is some positive value, you are still representing it as 0. You are actually underestimating. Now the input has become half LSB, you are still saying it as 0, 0, 0. Now input has become just more than half LSB, you are treating it as 0, 0, 1. So here we are underestimating the input, here we are overestimating the input. So here the input is actually half LSB, the output is still 0. So are we underestimating the input by half LSB? So that's what is this error. See here, this is my quantization error. That's what is EQ. When the input is, you have to compare to write this, you have to compare this and this. See here, let me just zoom only these two. See here, the input is 0, output is also represented 0, there is no error. The input is maybe half LSB, output is still 0, your error is minus half LSB, because input is half LSB, output is still 0, so you are underestimating it by half LSB. Now you can see here, just input is slightly more than half LSB, you are treating it as 0, 0, 1. But the input is not 1 LSB here. So even though just it is half LSB, just more than half LSB, you are treating it as 1. So you are creating, or you are committing an error of plus half LSB. So when the input is 1 LSB, you are representing it as 0, 0, 1. So that's why there is no error here. You can see at this point there is no error. So at exactly LSB points, the error is 0. You can see it is 0 here, 0 here, 0 here. Now since the transitions are happening at every odd number of half LSB, you can see the changes are happening here. So error, quantization error is varying from minus half LSB to plus half LSB. So corresponding to this quantization error, which is a noise like thing, because of which, and if the applied input voltage, suppose if the applied input voltage, suppose, let me just write it here. So what I'll do, I'll come here. Suppose if the input voltage is a sine wave of magnitude V reference by 2. If this is my magnitude, suppose if this is the peak of your sine wave, then its RMS, then its RMS value of that peak is V reference by 2 into 1 over 2. Okay, this is the RMS of the signal. This is Vs RMS. This is Vs RMS. Now we know that, okay, we have this type of error signal. We had actually this type of error signal. So this error signal. So if you can carefully look at the error signal shape, it looks like a sawtooth waveform. This sawtooth waveform has got a peak of, okay, let me write the peak of that. So what is the peak of this square, okay, sawtooth waveform? It's actually half LSB. This is the peak. So what is the RMS of a peak having half LSB when the waveform is like a sawtooth waveform? This is the type of waveform you have. So the RMS of, this is RMS of a sine wave, this is RMS of a sawtooth waveform. So then that will be peak is 1 LSB by root 3. This is root 3. So this becomes, okay, now it is 1 over root 2 root 3 LSB. So but what is LSB? We know that LSB is V reference by 2 power n into 2 root 3 is my voltage of the noise. Now if you find SNR, which is nothing but voltage of the signal by voltage of the noise, that is this by this, because here also you have V reference, here also you have V reference, you will end up with, of course, suppose if you just do the simple math, this SNR in dB comes out to be 6.02 n plus 1.76 dBs. Now where this n is number of bits, so 6.02 into n plus 1.76 dBs will be the SNR thing. So this is SNR max. This is a maximum SNR you can think of, having minimum error and maximum noise and maximum signal amplitude, maximum signal amplitude. Now, but in most of the cases, we may not get all combinations of the output when we are doing the analysis. So you can just have a look at this. Just have a look at this now. So let me just zoom this to a great extent. If you carefully notice this, if you just count the bits here, can you see for 0, 0, 0 you have this, for 0, 0, 1 is represented, 0, 1, 0 is represented for this input range, 0, 1, 1 is represented for the entire range of the input voltage from here to here. But if you actually see, 1, 0, 0 is not at all the output of a particular ADC. This is actually a missing bit. And you are having 1, 0, 1, and you have 1, 1, 0, and you have 1, 1, 1. The point here is, while seeing the ADC output of this simple 3-bit ADC, I am not getting the count of 1, 0, 0. So this I call it as missing code. This missing code is due to increased quantization error. You can see the earlier, maybe if I show you the quantization errors earlier, the transitions, can you see this was always 1 LSB bit, 1 LSB bit, 1 LSB bit. The width of this signal when it is there in a particular bit, can you see it's always 1 LSB. But if you see this is there for more than 1 LSB. Can you see for almost 2 LSB change in the input voltage, the output is still represented as 0, 1, 1. So this is an error. This will end up with a increased quantization noise. That will reduce my signal to noise ratio. So what I'll have now is, for a given ADC, there will be a signal to noise plus distortion ratio in dBs. This is SNR max you can think of. So assume that if n is equal to 10 bits, so then what is SNR max? SNR max, so this comes out to be 6.02 into 10 plus 1.76. So okay, 6.02 into 10 plus 1.76. Is it 1.76, 1.74? Okay, let me just do this. This is 61.96 dBs. Let me just verify this. Okay, where is this? Maybe somewhere here. Just give me 1 minute. Okay, here. It is 1.761. Okay, let me just go back to this. Now, if n is equal to 10, I'm going to have SNR max as this with an error of plus or minus half LSB, which is not having any miss in the bits. Okay, all combinations. Okay, for 10-bit we are supposed to get 1024 combinations, starting from all zeros of 10 bits to all ones of 10 bits. So none of the bit is got missed if the SNR is this much. Assume that there is a distortion, there is an error, there is a fault in your ADC, and you got the SNR of a real ADC comes out to be 58 dBs. If it is 58 dBs, which is certainly less than 61.96, for again same n is equal to 10 bits, I want to find what is effective number of bits and how many bits I want to miss. So what is this ENOB? ENOB is nothing but the value of number of bits that will be practically possible if the signal to noise ratio is reduced from an ideal value of the expected, okay, 61.96. Now this ENOB, effective number of bits. So this is effective number of bits is nothing but n value. So here just get the value of n here. It is now signal to noise ratio plus distortion minus 1.76 divided by 6.0. So this is actually ENOB. ENOB is this. So for this 58 dB, how much is this? Is it not 58 minus 1.76 divided by 6.02? Do have this as 9.342 instead of 10? Instead of 10 you have this. Then how many number of bits you are going to miss? So I need to find 2 power this ENOB. 2 power ENOB I have to do it. Okay, let me just take the entire 10 digits. It has made 2 to the power of answer. See this, how much you have? 649 bits you are going to have. 649 combinations only you will get out of 1024 including all zeros. So now what does it mean? So out of 1024 you are getting only 649 bits, so you will be missing 375 bits. So these many bits will be missed. This is missed bits. The number of bits that will be missing is 375 bits. So these many bits you want to miss. So that's what is the concept of this ENOB. ENOB is actually tells you how many bits you may miss. Okay, this was just an example. Just for 3 bit you are missing 1 bit. Just for 3 you are missing 1 bit. Okay, now can I actually find out what is ENOB here? So what is 7? Okay, now you are supposed to have 8 combinations. If you have only 7 combination, then 2 to the power of alpha A, 2 to the power of alpha A is alpha equals 7. Then I have to find what is A. A is actually equal to, suppose if A was now that's what the number of bits is coming out to 2.8073. This is 2. You can see here. So what I'm trying to do here is I'm trying to find what is ENOB for this. ENOB for this, out of 7 combinations you are having only, out of 8 combinations including this. Can you see here? This is 1, 2, 3, 4, 5, 6, 7. You are supposed to have 8, but this is missing. So then what is this ENOB? ENOB of this will be ENOB for this. So out of 8 you have only 7. So I want to find what is ENOB. So that can be easily found like this. So it is 2 to the power of n is equal to 7. So what is this 7 now? So what is this n? N is actually 2. Okay, I'm just doing it rawly. It is 2.8073. Suppose if you do, of course, so this will end up with only 7 bits. So out of 8 you are getting 7 bit means 1 bit is missing. So this is just to say what is ENOB for this example. Which example? This example. So ENOB of this example is 2.8073 instead of 3 bits. Okay, you will enjoy these things if you go deep and then try to understand. Thank you so much.